and the transition from the dense, soup-like atmosphere of the Florida coast to the hard vacuum of low Earth orbit is more than a change in scenery. It is a fundamental shift in the physics of fluid dynamics. While the Super Heavy booster relies on the brute force of 33 sea-level Raptors to punch through the thickest part of the atmosphere, the Starship upper stage enters a realm where the rules of engagement change. In the void, the enemy is no longer atmospheric drag, but the loss of potential energy. And to understand the necessity of the Raptor vacuum, or RVac, one must first visualize the behavior of a gas as it exits a nozzle. In the lower atmosphere, the surrounding air acts as a physical wall, pushing back against the exhaust plume. This ambient pressure keeps the plume collimated tight and focused. However, as the rocket ascends and the air thins, that external pressure vanishes. Without the atmosphere to hold it in place, the exhaust gas naturally wants to expand laterally the moment it leaves the engine. If the nozzle is too small, the gas escapes sideways before it can finish pushing against the engine bell. This is wasted energy, the kinetic leftovers of a combustion process that didn't stay in the system long enough to do work. And the geometry of performance, wide-angle vs. telephoto. In the world of optics, a photographer chooses a lens based on the field of view required to capture the subject. A sea-level Raptor is the telephoto lens of the propulsion world. It is tightly focused, designed to operate within a narrow, high-pressure corridor. Its nozzle is relatively compact, optimized to ensure that the internal pressure of the exhaust gas matches the external pressure of the atmosphere at sea level. In the Raptor vacuum, by contrast, is the wide-angle lens. Its most striking feature is its massive, flared nozzle extension. While the throat of the engine, the processor, where the combustion happens, remains largely identical to its sea-level sibling, the output peripheral is vastly different. The RVac nozzle is a towering cone of metal, designed to capture every possible joule of energy from the expanding gas. And by increasing the expansion ratio, the mathematical relationship between the area of the nozzle throat and the area of the nozzle exit space X allows the exhaust to continue expanding and accelerating against the bell for as long as possible. In a vacuum, there is no too big from a purely pneumatic standpoint. The larger the bell, the more work you can extract from the gas. The limit is defined not by physics, but by the structural constraints of the vehicle's diameter and the mass of the metal itself. And the physics of flow separation and structural integrity to the graduate student of aerospace engineering. The difference between these two variants is a study in flow separation. This phenomenon occurs when the pressure of the exhaust gas inside the nozzle falls too far below the ambient pressure outside. When this happens, the atmosphere literally crawls into the nozzle, peeling the exhaust flow away from the metal walls. This creates turbulent, asymmetrical loads that can vibrate an engine to pieces. And this is why a Raptor vacuum cannot be tested at full power at sea level without a specialized vacuum chamber. If you were to ignite an RVac on a standard test stand, the ambient air pressure would rush into the giant nozzle, causing the exhaust flow to separate violently. The resulting side loads would act like a giant, invisible sledgehammer, snapping the nozzle extension or shaking the engine mount until the hardware failed. And conversely, using a sea-level Raptor in a vacuum is like trying to run a high-end software application on a legacy 8-bit bus. It works, but it is woefully inefficient. Because the nozzle is too small, the exhaust gas exits the bell while it still possesses immense internal pressure. This is known as being underexpanded. The gas billows out into a massive, useless cloud the moment it clears the rim, leaving potential thrust and therefore specific impulse, or ISB, on the table. In the unforgiving math of orbital mechanics, where every second of ISB translates to hundreds of kilograms of extra payload, this inefficiency is unacceptable for long-duration missions. In environment-specific optimization, the hardware driver model. In computer science, we often use abstraction layers to allow the same core logic to run on different hardware. We can view the Raptor's powerhead, the turbopumps, pre-burners, and main combustion chamber as the core logic. This is the high-pressure engine that remains consistent across the fleet. And the nozzle, then, is the environment driver. When the Starship is in the operating system of the lower atmosphere, it utilizes the sea-level nozzle driver to manage the high-pressure environment. As it transitions to the operating system of the vacuum, the Starship switches its primary workload to the RVac engines. And this environment-specific optimization allows SpaceX to maintain a high degree of commonality in the manufacturing process. The guts of the engine are the same, which simplifies the supply chain and the log analysis of engine performance. However, the external interface, the nozzle, is swapped out to match the specific API of the vacuum. This modularity is a hallmark of the Raptor 3 architecture, allowing for a specialized fleet that shares a common DNA. And the thermal budget, cooling a giant in the dark. One of the most significant engineering hurdles for the Raptor vacuum is thermal management. In Chapter 5.2, we discussed regenerative cooling, where the cryogenic propellant is routed through tiny channels in the engine wall to soak up heat before being burned. For a sea-level Raptor, this is a well-understood challenge. But for the RVac, the scale of the problem expands along with the nozzle. And the surface area of the RVAC nozzle is several times larger than that of the standard Raptor. This creates a massive thermal budget deficit. There is more metal to cool, more surface area absorbing the radiative heat of the plume, and crucially no surrounding air to provide convective cooling. In the vacuum of space, heat can only be moved through conduction within the metal or radiation into the void. And SpaceX manages this through a sophisticated manifold architecture. The liquid methane is sent on a high-speed journey through miles of microscopic channels embedded in the nozzle wall. This isn't just about keeping the metal from melting, it's about energy harvesting. The heat absorbed by the methane actually increases the propellant's enthalpy, making the combustion process more efficient. And however, as the nozzle gets larger, the pressure drop within these cooling channels increases. If the methane has to travel too far, the pumps have to work harder, which eats into the engine's overall efficiency. The Raptor 3 vacuum variant solves this by using advanced 3D printing techniques to vary the geometry of the cooling channels. Near the throat, where the heat flux is highest, the channels are dense and high velocity. Toward the rim of the giant vacuum bell, the channels widen or change shape to manage the pressure flow, ensuring the entire structure stays within its safe operating temperature without overtaxing the turbopumps. And specific impulse, the currency of the void. In the previous discussion of the math of the bell, Chapter 6.4, we touched on specific impulse, or ISP, as the ultimate metric of rocket efficiency. It is essentially the miles per gallon of the space industry. For the Raptor 3, the sea-level variant achieves an impressive ISP, but the RVAC pushes this into the stratosphere, or more accurately, the exosphere. And by allowing the exhaust to expand to a near-perfect state, the RVAC extracts the maximum possible velocity from every molecule of propellant. In the vacuum, the exhaust gas is not just a byproduct. It is a precision-engineered stream of kinetic energy. The higher the exit velocity, the higher the ISP. And this efficiency is what makes the Mars architecture viable. When a starship is performing a trans-Mars injection burn, it is firing its engines for several minutes. During this burn, the difference of even 10 seconds of ISP can mean the difference between landing 10 extra tons of cargo or having to leave it behind on Earth. The RVAC is the high-efficiency mode of the Starship system, designed to squeeze every possible bit of performance out of the methane-oxygen reaction. And the challenge of the cold start in orbit, while the Super Heavy booster ignites its engines in the relative warmth of the launch pad. The RVAC must be capable of cold booting in the middle of a vacuum after hours or days of drifting in the freezing shadow of Earth. And this introduces the problem of fluid management. In a vacuum, liquids behave erratically. Without gravity to keep the propellant at the bottom of the tanks, known as settling, and without atmospheric pressure to keep it in a liquid state, the startup sequence becomes a complex dance of ullage burns and thermal conditioning. And small thrusters must first fire to create a slight acceleration, settling the liquid methane and oxygen at the tank outlets so the RVAC doesn't suck in a bubble of gas, known as cavitation. Simultaneously, the engine's nervous system, its sensors and valves must be pre-chilled or conditioned to ensure that the sudden influx of cryogenic fluid doesn't cause thermal shock. And the Raptor 3 integrated controller handles this hardware initialization autonomously. It monitors the health score of the propellant lines, ensuring that the temperatures and pressures are within the nominal window before commanding the high-energy spark igniters to fire. This is the orbital equivalent of a pre-flight check in a software deployment pipeline, ensuring all dependencies are met before the main service goes live. And the super plume and inter-engine interference. On the Starship upper stage, SpaceX typically employs a hybrid cluster, 3 sea-level Raptors for landing and low-altitude maneuvers, and 3 or more vacuum Raptors for orbital transit. This creates a unique cluster management challenge. And when the RVACs are firing, their plumes are so massive that they can actually begin to interfere with one another. Unlike the Super Heavy, where the atmosphere keeps the plumes separate, the vacuum plumes expand until they touch. This creates a backflow environment where hot gas can be pushed back toward the base of the ship. And the base heating problem is a significant concern for the Starship's aft section. Engineers must use thermal shielding and reflective coatings to protect the delicate avionics and plumbing from the radiative heat of these overlapping plumes. It is a high-density environment where the very efficiency of the engines, specifically the giant nozzles, creates a secondary problem of thermal interference. And managing this requires a coupled simulation approach, where the fluid dynamics of the exhaust are modeled in tandem with the thermal characteristics of the ship's hull. The Raptor 3 clean design again proves advantageous here. By minimizing external snags and protrusions, there are fewer places for hot gas to pool or create hot spots. And bridging the gap to deep space, the Raptor vacuum is the bridge between the industrial power of the launch pad and the scientific precision of deep space exploration. It is an engine that has been refactored for a specific use case, proving that the Raptor architecture is not a monolithic design, but a flexible platform. And as we look toward the Moon and Mars, the RVAC becomes the primary workhorse. It is the engine that will perform the lunar injection, the Mars arrival, and the Earth return burns. Its efficiency is the enabling technology that moves Starship from a launch vehicle to a true spaceship. and by optimizing the hardware for the vacuum, SpaceX has solved the efficiency gap that plagued earlier generations of multi-purpose engines. They have embraced the reality that different environments require different drivers, and in doing so, they have created the most efficient methane-burning vacuum engine in history. In this mastery of the vacuum environment is not just about physics, it is about the bottom line. Every ounce of efficiency gained in the Void is a reduction in the total cost of the mission. As the Raptor 3 matures, its ability to move massive amounts of cargo through the vacuum with minimal propellant consumption will redefine the unit cost of space exploration. This brings us to the ultimate realization of the SpaceX philosophy, the intersection of high-end engineering and aggressive fiscal optimization, explored in Section 10.3, The Economics of Space, how Raptor 3 lowers the cost to orbit.